Good morning, it's great to be here at CoreNet New Zealand. We work at CoreNet Architects, or short ZHA, as part of a team that specializes in analyzing buildings and users' behavior called Analytics and Insights.
We're both architects, so you might wonder what drove us into this more scientific direction. I focus on the impact of the built environment in people's behavior and the social and cultural implications of design, while Philip is on the computational side of things, dealing with tool development, algorithms, and data processing in the context of spatial design. For those of you who don't know ZHA, these are a couple of significant numbers about the practice, which is truly global one, not only in terms of project locations, but also its employees. Currently, 78 ongoing projects around the world, with 61 projects completed in 18 different countries. We work at all scales and in all sectors with a strong focus on highly expressive architecture. One of the most iconic projects is the Heydar Aliyev Center in Baku. But we will focus on the workplace-related projects of ZHA, like Wanjing Soho, a 3-tower mixed-use development in Beijing, China, or the Central Bank of Iraq in Baghdad, conveying its core values, solidity, stability, and sustainability. The BMW Central Building in Leipzig, Germany, where the factory assembly lines run through the office space, the Entreport House of the Port Authorities in Belgium, the Pierre Vive Building for the Department de l'Herald unifies 3 institutions within a single envelope: the Public Archive, a library, and the administration for the Department of Arts, Culture and Sport. Sberbank Technopark at the Skolkovo Innovation Center in Moscow, Russia, considered to be Russia's Silicon Valley, spanning almost 700 meters in the longest direction of the building. The Dominion Office Building is among the first of the new projects to be built for the growing creative and IT sectors in this primarily industrial and residential district in the southeast of Moscow. Infinitus Plaza in Beijing, Newtown, Guangzhou, China, which will be a campus of integrated buildings that combine intelligent technologies and environmental sustainability for LKK Health Products Group. King Abdullah Petroleum Studies and Research Center, which is executing the vision for a center-focused cellular structure of crystalline forms, a strong protective outer shell concealing soft, porous, sheltered courtyards within. So while early computational research at CoreNet Architects focused on fabrication and the delivery of solutions for the complex geometry problems that characterize the firm's projects, new research streams, such as the one conducted by our team, focus on user satisfaction and building performance data, as well as virtual simulations of users' behavior in office spaces.
Everybody knows that collaboration, strengthening the organization as a collective, and supporting well-being is necessary for a successful workforce, but how can we measure these things and derive valuable insights to make better design decisions? When we talk about collaboration, one of our basic premises is that physical proximity has a direct impact on communication potential, which has been further linked to collaborative behavior in the workplace. MIT professor Thomas Allen discovered how communication drops drastically as distance increases, and that it pretty much drops to 0 after about 20 meters, which is a 20-second walk. Let's look at an application of this theory. Consider a typical center core building, such as this one. How many people are in the range of any of these desk locations? Part of the development we are doing is a tool that calculates the distance from every desk in the building to any other point. In this case, interestingly, the worst places were the corners, visualized in dark red, normally reserved for the managers or team leaders. We can also analyze different furniture types. Here we found that a less rigid desk system increased connectivity by 10%. This is an analysis tool for visible area. We are looking into how much area and how many people are visible from every spot on the floor plate. The dark blue and red areas indicate bad and light blue good visibility. We can also look at how each space compares in terms of environmental qualities like daylight penetration and categorize it according to the British Council for Offices into Class A, B and C lit space. But it is not only about where we sit, it is also about how we sit, how many people are within our view. Did you know that Chinese way of dining on a round table is far superior to the Western way with rectangular tables? We created an algorithm that can measure the view quality and quantity across a table or a cluster of tables. So we can see here how very different the visual connections are depending on where you are sitting. In this case, what part of the table? On the round table, everyone has equal visual access to everyone else, whereas the rectangular table has more diverse conditions. So we can run this with different furniture layouts. The visual network is more continuous and much richer in the organic layout. So we have started to analyze and benchmark our completed projects to understand how they support this workplace variety. And also how all the things we have been measuring inform design decisions in the future. This is the connectivity analysis. As a result, we can see which areas best suit independent teams in the more segregated parts of the office and interdependent teams in more central locations. We can also look at aspects like the shortest path to the office entrance. And we are able to identify most public and confidential spaces, as well as where to locate most and least mobile teams. Similarly, how close you are to facilities like breakout areas or other amenities. This allows us to determine the areas in which you are most likely to encounter the least distraction and quieter zones, as well as the noisier ones. How much of your surrounding you can see and how well you can be seen from a given location determines how exposed certain areas are to the public sight, helping the planning process by identifying which zones can be used for more planned, confident meetings out of sight and zones for more informal, unplanned meetings in plain sight. Calculating the amount of daylight coming into the floor plate allows us to identify zones for different degrees of permanence. The best lit parts are great for spending most time at the desk, whereas zones with less daylight are better for short stay periods or touchdown zones. And also look at how different orientations of desks within these areas can affect visual connections with coworkers. As well as views, there's no point having a great view if your desk is facing away from it. The design analytics of past projects gives us a great idea of how specific design decisions supported or limited performance of space.
We know now how to measure and quantify certain human-centric qualities of space and can start to think of how to actually design spatial conditions with the outcomes of those qualities in mind. Considering the center core tower as our baseline, looking at the visible area parameter, with 57% average visibility, by just chamfering the edges of the core, we can increase visibility by 3%, or even more drastic changes, like splitting the core into 4 and pushing them into the corners, we can increase visibility by 33%. A more realistic option would be splitting the core into 2 and including an atria, which still increases visibility by 25%. Also, when we measure daylight, we find drastic differences across all 4 core positioning strategies. While the 4-corner core option has a high visibility, it lacks natural daylight. Our atria split core tower, though, has great daylight values. And the same for connectivity. While the 4-corner tower has a great connectivity outcomes, the atria tower's connectivity is decreasing by 19% comparing to the baseline. So now it's really up to what is important to us or a client, but this is really helping us to make informed decisions overall. For example, in this tower competition, we were able to rapidly assess a variety of core configurations and building envelopes to support decision-making in the early competition stages. The 18 design options in the last slide have been created manually, but what if there is still a better solution? This is an early version of an algorithm that can generate every core location and analyze it against every other. The example I'm going to show is for a square tower, with every core shape and location within a 50-meter grid for both a single and double core option, which is then analyzed with the objective to optimize daylight and cross-floor visibility. At 1 option per second, it took 27 hours for it to generate, analyze, and compare all possible 100,000 options. Manually, if we were to draw up and analyze 40 simple diagrammatic options a day, it would take about 10 years. The majority of projects, especially at ZHA, do not come close to a 90-degree angled square, so we had to come up with a solution that would work with any other shape. This here is a particle system-driven HR and core placement tool, self-adjusting, again with the objective to optimize daylight penetration and cross-floor visibility, as well as escape distances.
Understanding how space impacts people is one thing, but the other is measuring the behavior of people in space. Learning from it and relating it back to the spatial analysis is another interest of ours. IoT devices like sensors allow us to look in more detail at the workplace than ever before. We have deployed sensors in a series of environments, one of which was an exhibition held by 3 of our research teams, Code, VR, and Analytics and Insights. We have attached smart cameras to the ceilings of the exhibition space. The image of the camera looks like this. The cameras measure movement over time. In order to gain insight from the readings, effective data visualization becomes key. Here we are looking at 670 hours of occupancy sensor data about exhibition attendance patterns in 10 seconds. Furthermore, we can look at how the space was used over an average month, each color representing one exhibition space, while the orange line is the circulation movement. Visitor peaks are in the morning and afternoon, as well as the late evening. And finally, we can compare which of the exhibitions had the highest attraction or popularity. We deployed the same cameras in our main breakout and reception space in London and are able to map interaction levels using movement patterns. Or environmental sensor reading from one of our design studios visualized as a 3-dimensional landscape of temperature, light, and air quality that can be easily understood by building operators. And make this data available to the end users of the space, such as temperature, daylight, CO2 levels, and humidity. Going forward, if users are able to input their own preferences, this can suggest what location might be most comfortable for them. So what can we use these measurements for as workspace planners and designers? By bringing all this data together, we can start to understand the workplace much more clearly, not just on building and floor plate level, but on an individual level, creating a unique workplace signature at every individual work setting. So we can collect data on people's preferences and match them to the right workplace. It's not enough to look at the individual alone. Communication and collaboration networks are highly complex, both physical and digital. Research has shown that email communication and face-to-face communication are almost identical. We can interpret this as an opportunity to provide spaces similar to the way people interact. This is a genetic algorithm that works out the best placement for 19 people based on their 5 highest rated people in terms of communication. We have just shown a group of 19 people, but what if we have to place 268 people on the floor plate? There are more seating combinations than stars in the universe. One of our solutions to the problem is to use a divide and conquer strategy.
Ultimately, we're using these tools to build a spatially intelligent model and automate designing and the overall planning process. We are striving to create a system which is integrating the multitude of parameters and influences we have been presenting to you, able to recursively react to new input, learning over time. We started investigating this by developing a matrix of furniture typologies that could be adaptively interchangeable and scalable. constantly updatable from a catalog of activities. We started to use algorithms from the physics field, like particle systems, to deploy furniture based on the design preferences input. It could continue to adapt, evolve, and improve through the cycle of the workplace. Multiple diagrammatic options could be generated virtually instantaneously, creating a more efficient and rigorous design process. This can then be designed further once the preferred option has been established. And design would not need to stop once the workplace is occupied. The design could update itself based on new density requirements or mix of program or collaboration needs. Based on sensor and user analytics, the design could even suggest its own updates periodically. This seems to be quite close to reality, and while a designer would sit on this for hours, our algorithm was able to produce this floor plan in a couple of seconds. We can make changes on the fly and reevaluate the adapted furniture placement. I believe this is a pioneering time in workplace architecture, and it's been an honor to share some of the excitement we feel at the Analytics and Insights team at Zaha Hadid Architects. Thank you.